Exercise 2158 is asking you to make DEET. DEET is the active ingredient in many insect repellents, such as OFF. Now they're saying if you start with metabromotoluene, which they give you here, and using any other reagents of your choice, how would you make DEET? And you can see what DEET looks like over here. So that's that. But why would you limit yourself to that? Let's go one step further. How could you make DEET just from the vapors of gasoline? If you just had benzene, how could you make DEET out of that? Well, first we'll talk about how to make this M-bromotoluene, the metabromotoluene, and once we have that, we'll talk about how to turn that into DEET. And when we're looking at how to make this metabromotoluene, we have two things we have to add. We have to add a bromine, and we have to add a methyl group. Now, when we did these reactions on the aromatic substitution reactions, where we put things onto the benzene ring, we looked at these branches in two parts. First, just what is the recipe for putting the branch on? And second, what order do we have to put them in order to get them in the right place? So to put a bromine on a benzene ring, you'll remember you need Br2, but with a catalyst, FeBr3. And then to get a carbon on a benzene ring, you could either do Friedel-Crafts alkylation or Friedel-Crafts acylation. Now, to choose between the two, you want to think about the relative placement of the two branches. These are 1, 2, 3 carbons away. In other words, these are meta. But the halogens, chlorine, bromine, iodine, those are ortho-para directing. So you definitely can't put the halogen on first, because then if you try to put the carbon on, it would go at the ortho positions or the para position, but not the meta position. The only thing is, alkyl groups are also ortho-para directing. So we can't just put an alkyl group on. What we can do instead is first do an acylation. And you'll remember that is a moderate deactivator, that is meta-directing. Once we have that on, we could add the bromine, it'll add to the meta position, and then we can reduce that and get rid of the carbonyl. So, we can do a Friedel-Crafts acylation. Now we only want one carbon, so we could have a double bond to the oxygen, single bond to the chlorine, and actually, let me put that on the other side. Whatever bond you want to go to the benzene ring, that's where you put the chlorine. So we have a chlorine, we'll have a hydrogen on the other side, and we want to make sure to use the catalyst, AlCl3. So you've drawn the mechanism for this on a previous exam. That puts that acyl group onto the benzene ring. And we're replacing the bond to the chlorine with a bond to the carbon. Now that is a meta-director. This, if you have a pi bond to an electronegative atom on the benzylic position, that's a moderate deactivator and a meta-director. So once that's there, we could add the bromine. We could do Br2 and turn it into an awesome electrophile by adding the FeBr3 catalyst, and the bromine will add meta to our acyl group. And now we just need to get rid of those bonds to oxygens. If you're trying to reduce an acyl group that is conjugated with the benzene ring, there's a special recipe for that. You'd use a zinc-mercury amalgam, so that you just take zinc metal and smush it together with mercury metal. You get that amalgam, and you dunk that into HCl acid, and that'll reduce the carbonyl that's conjugated with the aromatic ring. So now we have our metabromotoluene. So you can see how we can make metabromotoluene just from the vapors of gasoline, benzene. Okay, well once we have this, how do we turn this into DEET, insect repellent? Notice that we already have this part of the molecule. What we need is this rest of it. Now the first thing we'll notice is we need to form a carbon-to-carbon bond. And we have a bromine. Well, bromine is strongly suggestive of a Grignard reagent. Why not dunk some magnesium in there, and then we'll have this Grignard. That Grignard is really a carbon nucleophile. Effectively, you have a lone pair there and a negative charge, positive charge on the magnesium that's stabilizing it. Well, what do you see in this carbon? I see a carboxylic acid derivative. Carbon double bonded to oxygen, single bonded to an amine. That's an amide. So wouldn't it be convenient if we could have our Grignard attack a carbon that creates a carboxylic acid? But what carbon creates a carboxylic acid when it's attacked by a nucleophile? That is carbon dioxide. If this nucleophile were to attack carbon dioxide, one of the pi bonds would break, and we'd get a carboxylate. We would get a carboxylic acid, but where the hydrogen is replaced by a negative charge on one of the oxygens. And so you can follow that up with some acid, an acid wash, or a water wash, and that would turn that carboxylate into the carboxylic acid. Okay, well now let's compare that to what we are dreaming of. When we compare that to DEET, all we have to do is a nucleophilic acyl substitution, because this DEET has this nucleophile come in, this nitrogen nucleophile come in, where we have an OH. Now, as we've seen before, you can't just, if you look at this nitrogen nucleophile, nitrogen with two ethyl groups, the bond to the carbonyl is really just a bond to a hydrogen when that's on its own in a molecule. So you can imagine that's our amine. But we can't just treat the amine, the carboxylic acid with the amine. That's for two reasons. One, the amine has that lone pair that's basic. This is just going to steal the acidic hydrogen from the carboxylic acid. It'll react with that before it attacks the electrophile. The other issue is that the electrophile, the carbonyl carbon in a carboxylic acid, is not the best electrophile because these lone pairs on this oxygen are allylic to this pi bond, and so they, through resonance, donate electron density toward this carbonyl carbon. So it's not the best electrophile in the world. It's a decent one, but not the best. And this is a weak to moderate nucleophile. So that's not going to be a very efficient reaction. So we need to solve two things. We need to get rid of the acidity, and we have to make this more reactive. We can do both of those things with one fell swoop. Turn the carboxylic acid into an acid chloride by using thionyl chloride. So now we have the acid chloride. And once you have the acid chloride, well, then you can treat it with this nitrogen nucleophile, and you'll just do a nucleophilic acyl substitution. Now, you would either want to treat it with excess of this or with some other base. I would treat it with excess of that, so you don't have to worry about any competing reactions. And the reason why you want excess is because after you add this first equivalent on, there's a hydrogen there that gives this a full positive charge. So you need to do a proton transfer. A second ammonia could steal this H plus and have the electrons snap back onto that nitrogen, stabilizing the charge there. Ah, and lo and behold, there is a DEET. So that is DEET. So we were able to make DEET. You now know enough chemistry to make DEET from the vapors of gasoline. First, we did a Friedel-Crafts acylation. Put this acyl group there. We had to make it an acyl group because that's a meta-director, and we need the bromine on the meta position. So we added the bromine using Br2 and a catalyst that turned it into a really good electrophile so that even benzene would react with it, FeBr3. That added on the meta position. Once that was added, we needed to get rid of that carbonyl because it's not in our product. And so we reduced it with a special recipe that reduces these carbonyls conjugated with a benzene ring. Zinc-mercury amalgam in hydrochloric acid. Well, so much for that. That gave us what they really told us to start with here. That gave us metabromotoluene. We know we wanted to add stuff where the bromine was, and specifically we wanted to add a carbon. So we turned the bromine into a Grignard by adding magnesium. That gave us our Grignard reagent, and we were able to create a carboxylic acid and add a carbon at the same time by reacting our Grignard with carbon dioxide. That gave us a negative charge, but we stabilized it with some acid. So now we had the carboxylic acid, and all we had to do was replace the OH with our amine, and we'd have DEET. So we had two problems. We couldn't just react it with the amine, because the amine would steal the hydrogen as a base, and it would also not react very efficiently with the carbonyl carbon. So we took care of both of those problems by turning the carboxylic acid into an acid chloride by adding thionyl chloride, SoCl2. This is now an awesome electrophile. There's no acidic hydrogen there, and so we could treat it with excess of our amine, and we do a nucleophilic acyl substitution where the chlorine gets replaced by the nucleophile. And there it is, DEET, magic. Something like a chef and a magician, something in between a chef and a magician. We made a transformation that people in the 1600s would have thought we were witches for, and yet it's completely real. So there's an example of making an industrially useful compound from something that's maybe less useful and less expensive.